Good afternoon, everyone. Our talk is Autonomous Mobility at Zoox meets Ray. I'm Eli. Ron will be giving the second half of the talk today. I've been with Zoox since 2019, so a little over 5 years. I've had a number of roles at the company, manager of ML platform. I'm currently an individual contributor on the ML platform team. I focus on ML training. Ron is coming up on 2 years. He's also a staff software engineer on the ML platform team. His focus has been on inference and GPU performance optimization. Zoox is an autonomous mobility company founded in 2014. As you might be able to tell by the image there, we have a focus on purpose-built robotaxis. Okay, so at Zoox, we use Ray for quite a bit of things. We use Ray train, data, tune, serve. But the ways that we're using Ray are not particularly interesting, I think, for a general audience like this. Basically, we are using Ray to do the thing that it says it's good at, and it's good at doing it. So, you're probably wondering, okay, what is this talk going to be about then? Let's get into this. But first, let me recap what 2014 was. That was a decade ago. Happy by Pharrell was the #1 single. The top of the box office was the first Guardians of the Galaxy movie and the third Hunger Games movie. The ALS Ice Bucket Challenge was taking over social media. A little bit more on topic, generative adversarial networks were introduced, and Kubernetes was announced, but 1.0 didn't come out till the following year. The GPUs of the year were the NVIDIA GeForce GTX 980 and the Tesla K80. So all in all, it was a different era. In that decade, Zoox has built a lot of on-prem hardware. You can see some of that in the picture here. We have an AWS compute cluster controlled by Slurm. We've built wrappers around Slurm, storage systems, remote build execution, ML training clusters, simulation clusters, and all of that was in place before we decided to introduce Ray. If we can use Ray, it's almost certainly that you can introduce Ray into your environment as well. We feel that the integration work that we had to do in order to make it work for us was reasonable. And like I said, the features work as advertised. So what we're going to do here is we're going to talk a little bit about some of the main challenges that we faced introducing Ray. All right. First is, like I said, we use Slurm. The vast majority of our compute is managed by Slurm. If you're not familiar with what Slurm is, it's cluster management, job orchestration software. Started at Lawrence Livermore over 20 years ago. It's the kind of software that's in use by more than half of the top 500 supercomputer list. It can be a little rigid when it comes to scheduling. It's very much you're going to get 4K CPUs and 1K GPUs for 48 hours. If your job takes 49, too bad, we're killing your job. And you're going to have to figure out what to do with the pieces that are left over. It approaches scheduling as a bin packing problem. And so if you have 900 GPUs free right now, it's not going to start your job because you said you needed 1,000. So it's not really designed for an AWS spot instance kind of world. Which means that it's kind of a mismatch between how Ray thinks about the world, which is, I think, a much more modern approach. So compute is allocated per job, and it does not persist once the job is completed. So trying to debug an error live, by the time you realize an error has happened, it's already torn down the job and is putting the next thing on that compute. In terms of Ray, the head node is going to go away at the end of the job, unless you have a head node living somewhere else, which we'll get to in a minute. Slurm has this concept of being able to run multiple jobs on a single node at the same time. We ended up having some port conflicts with Ray with that. And I'll talk about this more in a minute, but overcommitting resources can be very easy in this kind of situation. Also, Slurm doesn't really have a concept of adding compute to a job post-launch. So you start with the resources you're going to end with. Okay, so let's talk about how we can deal with the lack of head node persistence. Solution one is my favorite kind of solution. You just ignore the problem. And that's somewhat flippant, but it's true. You can actually get a lot of valuable work done using Ray without a persistent head node. You just set up and tear down your entire cluster, your quote-unquote entire cluster in the compute that Slurm allocates. And you, like I said, you can get a lot done without needing to solve that particular problem. What we ended up doing was taking all of our array initialization code and centralizing it, then standing up a persistent head node on a different piece of compute, not managed by Slurm. And then pointing all of that centralized initialization code to that new head node. One thing I do want to note that since we have multiple Python and Ray versions in play, we actually needed multiple head nodes because you have to match Python and Ray versions exactly. I also mentioned that the Slurm has this shared compute. If you're only going to be using half of the CPU cores on a node, Slurm will happily put another job on it. Since Ray has a similar concept, these two concepts kind of conflict with each other a little bit. Trying to spin up multiple Ray jobs on a single node ended up having port conflicts because Ray wants to use the same port by default. So we had to do some work in order to tell each Ray job what ports it should be using. Obviously, there's a lot of different ways that you can solve this. One thing I'll note, pure random does work, but eventually the birthday paradox is going to mean that you're going to start having flaky failures where two jobs try and use the same port. What we ended up doing was something fairly simple where we just check for open ports first. We're not often kicking off multiple jobs on the same node at the same time. So if a node was open, that was good enough. I mentioned also overcommitting resources. Slurm is really good about matching job definitions to your actual available hardware. People are bad at matching job definitions to the actual needs of the job. Now, this is not explicitly a Ray issue, but Ray is really good at using all of the resources on the node that it's running on. And so if you're not careful about limiting Ray to what Slurm thinks the job is going to use, if a second Ray job ends up on the same node, all of a sudden you now have two jobs, or two Ray tasks all competing for the same resources. Like I said, that's not really a Ray issue. It will cause problems if your organization isn't disciplined about it, though. I will remain tactfully silent on whether it was a problem for us. Okay, so I'm going to talk a little bit about some specific projects that we've worked on, just to kind of give you a sense of what Ray has actively enabled for us. Zoox uses PyTorch Lightning pretty extensively. The Lightning data module is used by many teams, and we have, for the teams that are using Lightning, essentially universal use of the Lightning module and Lightning trainer. The launchers for those training jobs are a lot more varied. Many models just have custom one-off code to go ahead and launch the training job. There are some per-team wrappers around Lightning to kind of standardize things a bit. But across all of those, the support for basic infrastructure features was wildly inconsistent. Some jobs would be able to do multi-node training, some would not. Fault tolerance, being able to repeat jobs, common integration with our experiment tracking, all of that kind of stuff was kind of all over the place. I will note here, though, that PyTorch Lightning has excellent support in Ray. It's worked flawlessly for us. We take a PyTorch Lightning trainer, pass it through the ray.train.lightning.prepare trainer function, and then the Ray train torch trainer just worked. We were able to spin up a standardized set of multi-node training, et cetera, very easily with this. What we ended up building, we call the Zoox training framework, or Z-train. It brings all of our users' Lightning modules to a standardized infrastructure layer, requiring few to no changes to those existing Lightning modules. And what it does is it allows us as an ML platform team to uplift all of those models with valuable features. Like I mentioned, being able to restart after an error, multi-node training, whenever we introduce a new instance type on AWS, making sure we have the networking configured properly, all of that kind of stuff. All right, so we've talked a little bit about legacy infrastructure, about how Ray fit into our decade-old tech stack. We talked a little bit about PyTorch. Now I'm going to have Ron come up and talk about what it looks like when we do a Greenfield project.
Thanks, Eli. So Zoox has been around for 10 years, and it's not exactly a new startup. Not every day we get to work on a Greenfield project. But when things like that happen, the team really got excited and wanted to take full advantage of that. So enter ZServe. So the reason that Zoox has not been thinking about a cloud-based serving framework for at the beginning of its funding is because we are in a safety-critical domain. And imagine you sitting in a robo-taxi and somehow there's a data outage and there's a wait for connection to the machine learning model in the cloud. there's a spinning wheel. It's probably not the best user experience Zoox wants to give to its customers. But in recent years, we see an explosion in the AI applications. So not everything has to be computed on the vehicle, right? So there are plenty of use cases where we can have computation done off vehicle. For example, simulation data. For example, the logs that are generated from the actual vehicle runs, we can do a post-mortem analysis, and that does not have to take place on vehicle. So it is really a good time to start thinking about an inference service that runs in the cloud 24/7. And so we decide to start this ZServe project by building something on top of ZServe. And also, it runs on AWS EKS clusters. And right now, I'm happy to share that it's serving a number of models in production. So in a nutshell, ZServe is a ML framework neutral and data format agnostic. So we cannot predict future, especially for such a rapidly evolving field. So the best way to predict future is stay framework agnostic and also data format agnostic. It is also language neutral because we built it on top of protobuf. And also the Tensor I/O format are compatible with TensorFlow, so that if you want to really visualize it with TensorBoard, you can do it. Also, it works really seamlessly with ZServe because it's a Greenfield project. We do not have to carry the legacy, such as running things on Slurm. We can work with Kubernetes. And also, the beginning of the project is really driven by lots of internal needs. Our internal project and team have a lot of need for PyTorch and NumPy. That's why we have building first-class support for PyTorch and NumPy. But in the future, if JAX come around, we can happily support JAX as well. That's no problem, because it's easily extensible for both public and proprietary data formats. And here's a typical journey of a query. And so you have on the client side, you encode some of the input into a serializable format that we call Z request. You can transmit that over the network, and which gets unpacked on the server side, and you can either invoke the CPU or the GPU, get inference down either way, and then have it shipped back, and also have it decoded on the client side. And that's how a typical query life journey looks like. So far, I have described a very standard way of doing inference service, nothing special. However, there's a bit of a surprise that we do in some of the projects we have with the client. So basically, we discovered that in terms of the number of lines of code that cannot be really reused across model, because these number of lines of code that we set here are really model-specific code. For example, we do not include the serialization engine we have built for ZServe because that is completely generic, reusable. We certainly would not include any lines of code for PyTorch because that couple million lines of code is completely reusable across different models. However, there's always a bit of a code that you cannot really generalize across the model boundary. You have to written those test cases for the model, and that cannot be transferred to yet another model because it has different architecture, different layers, right? So it's hard. But when we look at this line of code statistics, we kind of think that you need roughly about 500 lines of code per model. And then also for each model, if you want to build a Docker image, it's about 16 gigabytes in size. But we really have a handful of models. That handful is an understatement. But imagine you can do the math and multiply by 10, you got like 5K lines of source code, and that really adds up, right? So here's one way that we approach this problem, and just similar to how you can customize a Ray cluster by configuring things in the YAML file. Same idea. But we want to go one step deeper in terms of asking the user to specify not only the model trivial, like where to get the S3 bucket and where the model file are located, but also ask the user to define the inputs and outputs in a declarative fashion. And therefore, we get lots of benefits out of this declarative approach. First of all, we get an application-neutral client and server pair. So you don't have to engineer different client server for different models. Just one version of client, one version of server. That's all you need. Also, automatically, we will get the test vector generated for your application. Because you tell us how the shapes of each tensor looks like, we will be able to not only generate a test case, test vector for you, but also when you supply us with different tensor shape, we'll tell you which dimension, which tensor key has it wrong. So you will get very informative error messages that way. And also, we have consolidated all our models and applications in a single Docker image that is ready to deploy. So that makes really Docker deployment much easier. So there are other benefits of using our so-called model-based ZServe on Ray. And I like to always cite numbers. Previously, I cited that 500 lines of code is needed per model. How much lines of code is needed under this new model-based service kind of architecture? Well, looks like we only need only 5 models, which is about 100-fold reduction. Just like the cost of tokens, price per token has come down 100-fold. We also want to do something drastic, like 100-fold reduction in number of lines per model. But it's always the same 5 lines, and that's interesting too, because if it's different 5 lines, you need to say, well, which 5 lines for me, because I need to find out my 5 lines of code. But in most cases, unless you are very particular about how you name those model names, you can literally copy from one model because it's the same 5 lines of code. You dump in, and there you go, you have another model created. Now, wait a minute, we have different model use cases. We have different inputs, different outputs. How could you make sure it's always the same 5 lines code? Rest assured, because those 5 lines are non-model specific. It's always the same 5 lines, like you want initialize model, encode the request. But the request can come for different forms. How would you make sure that the same line of encode request meets your need? Well, because we have abstract away all the model-specific logic into a PV text-based configuration file. In that file, you can specify 1 tensor in, 2 tensor out, 2 tensor in, 1 tensor out, 1 tensor dictionary in, 2 tensor dictionary out. All the combination thereof will support that. But the magic is you only need to configure that in your PV text file, which does not count as Python lines of code. It's PV text, right? Or any configuration. So that means we have higher software quality because now we have a single source of truth for model inputs and outputs. And before that, we have to engage our customer teams asking for, can you tell us what the tensors and what are their dimensions? And they will reply on a Slack channel, which might have typo errors, right? Now we have a single source of truth for where the model inputs and outputs come from, and also because these are always tested in our continuous integration system 24/7. So there's no chance that this can depart from the source of truth. And also, last but not least, because we are a small team, Eli and I, plus a few colleagues also in the audience, we're a small team. We are supporting maybe more than a dozen AI teams. So in order to make this whole approach scalable, we believe that we need to have decentralized model ownership, meaning that we provide them with the engine, the tool, but we're not going to walk the walk for them, do lots of hand-holding for them. We have to let them being able to, the customer team, be able to customize models and do their own model creation. So that's what we think that decentralized model ownership will really make a difference. Last but not least, we also achieve better observability because with model-based helps observer, we can tailor different alerts to a specific application and model because now we know the inputs and outputs, we know the criticality of the models, so we can better tailor our alert logic like Grafana alerts to the needs of our applications. So in conclusion, we think that Ray really integrates well with a range of environments from legacy systems that are built on top of Slurm and HPC, in the case of Ztran, or for a more modern approach, such as ZServe, which is built on top of Kubernetes and EKS clusters. We're very happy with how Ray is powering our ML platform because it provides unified infra support. We do not have to use different sort of substrates and infrastructure layer. We just build our competencies all on top of the wonderful products that NScale engineers has built for us. By the way, I want to give a shout out to the NScale engineers. You guys really have done a terrific job. Thank you. We also, both the training and the serving framework have embraced a declarative framework and workflows that makes it super easy for our customers to customize their logic, to be creative on their side without really getting in the way or without letting our service framework get in their way. So I guess the biggest surprise for using Ray so far is there is no surprise at all. It just works. And that's the best kind of surprise that we want to see going forward. Last but not least, and also as a shameless plug, we are hiring the ML platform team, and also I would say the entire infra team is hiring. So if you're interested in autonomous driving, mobility as a service, or just machine learning in general, come talk to us. Thank you. And then Eli and I are happy to take questions.
Thank you for that great talk. For questions, please come to the middle and use the mic. Thanks.
Thank you for your presentation. Can you please elaborate about the hardware, kind of hardware do you use in your vehicles? From chips to sensors?
So we have an incredible amount of compute in the vehicle. We have a lot of NVIDIA compute. We have LiDARs, we have radars, we have cameras. I have lost track of how many of each, but tens of different sensors all over the vehicle. You can see on the top corners, there's sensor pods that have multiple sensor modalities on them. In terms of compute, I don't believe I'm at liberty to say exactly what it is that we're using, but you can think of it as the equivalent of a rack mount server on wheels.
Again, thank you for this great talk. I just wondering, for your ML compute for the data processing, are you using any like traditional ETL engines or like Spark or anything like that? Yeah,
so it's actually a different team that handles that, so I'm not going to be able to talk to in depth. But yes, we do have fairly heavy ingest processes where we pull data off a vehicle and then go through multiple stages of processing using Databricks. Any other questions?
I guess as a follow-up, some of the ZServe use cases were motivated by some of the data ingestion process that we have. So it's ML and data pipeline processing is kind of a converging in Zoox.
Cool. Thank you all.